Thank you everyone for joining us. Today I'll be telling you more about IntelliSuite. It's an end-to-end solution for MEMS design and analysis. So first I'll just give an overview of all of the software modules, and then we'll go through some live demos, and then we have some hands-on training examples as well. So I'll start out just giving an overview of IntelliSuite as a whole, and then we'll go more in depth with device simulation and then the clean room tools for process simulation. So just a little bit about IntelliSense as a company. We were founded in 1991 as a spin-off from an MIT lab. We were the first completely integrated CAD tool for MEMS. We were acquired by Corning, and they acquired our software portion of the company as well as our fabrication facility in Wilmington, Mass. We later reacquired the software portion, and now we focus on our MEMS software. And more recently, we developed a fabrication facility in Nanjing, China. So we provide our users with both software and some low-volume fabrication services. It appears that my presentation has some timings in it. So along with these software tools, some users will come to us and they'd like both a software solution and some help with their design or their fabrication. So we're usually able to provide all of that with both our teams in the US and in China. But today we'll be focusing completely on the software. So just an overview of the architecture of IntelliSuite. We start out with our process tools, and then we have some geometric tools for CAD modeling. Then we have our device level tools, so for multiphysics simulation. And then we have some system level tools. Our main one is called Simple. And so from end to end, there's a tool that can help you with every phase of your design cycle. Here's just another overview. On the left, we have our schematic tool called Simple for behavioral analysis and system level analysis. Then we have Blueprint for layout. Our collection of clean room tools, and this is a collection of both standalone tools for certain processes, and then we have some other tools for visualizing an entire process flow. Then we have our fast field multiphysics tools. There's one that I'll be going over today called thermoelectromechanical. We also have two other tools, one for biomems and microfluidics and another for electromagnetic analysis. And then on the right we have EDA Linker, which can help you link your simulations with other simulation tools like Cadence or Simulink or anything else that you might be using. So in our design, we take two major approaches. We have our top-down design flow, and this is where we have all of our process flow information, our material information, and from here we're able to generate a mask layout, generate a design, and then after that we can mesh our model for 3D verification in one of the FEA tools. This is where you would start with our behavioral analysis tool, Simple. So you would have a faster simulation, but it would be slightly less accurate. Then we have our bottom-up design flow. And this is where we would have our 3D model from the beginning. We design it, and then we create a mesh structure and study it with our multiphysics tool. So this is more accurate, but it tends to be slower. So what we try to do is provide tools that can overlap these so that the user can choose any tool flow they want, whether they want to start with their layout and their process information or whether they want to start with their 3D model. In the end, you can end up using either of the tools, either the behavioral analysis tool or one of the multiphysics tools. So just a little more in depth, the categories of our tools. It's four main categories. It's Blueprint for Blueprint for layout. Then we have Simple for behavioral analysis and schematic design. This is where a lot of users will begin when they have a concept or if they want to see how their device acts as part of a larger system. Then we have our fast field multiphysics tools, and these are just some examples of some things that we've simulated using TEM, or thermoelectromechanical. Then again, we have our cleanroom tools. So here are just some images. Most of these are from FabViewer, which I'll go more in depth about later. On the top left, we have one of our newer features in Intella Etch. We have some quartz etching capability. So as I mentioned before, the presentation will focus mainly on the device simulation with multiphysics tools and the process simulation aspect. So just a quick overview. In the beginning, I have a video showing a typical IntelliSuite tool flow and just how a user would get from point A to point B. And all right. So first here we have a pressure sensor that a user had a GDS layout in LEdit. And here we're able to import the GDS file using Blueprint. And when we import different file types, generally we're able to maintain all of the same layer information when we import and export. Now we're just importing it again to show that the file is the same after the conversion. Next, we have a process flow that we've built up, and we can bring in our mask from Blueprint. Then we can visualize in FabViewer. So here we'll visualize each process step. And using this tool, or using IntelliFab that was shown before, we're able to choose between FabViewer and FabSim, our two process flow visualizers. From there, we can also go back and easily edit our layout, or we can go directly to the multiphysics tool, and it will generate the 3D model based on the process information and the layout that you've input into IntelliFab. So that's what we're doing here. And then it will run through Hexpresso, our mesh engine. So in there, we would set any sort of mesh parameters or define areas where we want a more refined mesh. And like any meshing tool, your mesh time will be a little bit longer for more complex structures. So this is the longest part of the video, I promise. All right, once we're done meshing, we can open it with TEM. This is our most widely used multiphysics tool. As I mentioned before, we have two others, and they all work very hand in hand. The file compatibility is all there, so you can go from one tool to another tool very easily. So here, first we're going to set an initial stress after choosing our simulation settings. And like any multiphysics tool, I know most of them are structured where you have this tree on the left where it will show you all of your entities and your boundary conditions and loads. So this is similar. So once you set your load or any boundary condition, you'll see them appear on the left, and then you can easily go back and edit them if you need to change a value. And here we can view our material information in this tool called MEM material. In here we have a vast material database. Sometimes users will be working with materials that aren't in there. So we make it easy to import your own material information, either if you're basing it off of an existing material in the database or starting from scratch. And that's something our team is always able to help with. If you have a material that isn't very common, we can usually incorporate it into the tool. Here we're viewing the Z displacement and the stress component. Next, we're performing a heat transfer analysis. So we'll basically be doing the same simulations, but with more realistic temperature information. Oh, by the way, we did cut the simulation time out of the video, just because it can sometimes take a while. It definitely depends based on what type of simulation you're running or how complex your mesh is. This one does not take that long, but it's too long for this. So here we're viewing the displacement again, and then the stress. Next, I just want to give a quick overview of Blueprint because it's a major component in every single one of the IntelliSuite tools. Most of them you're working either with a mask or a multi-layer layout. So Blueprint is a basic layout tool. It is compatible with DXF and GDS2 files, which are common. A lot of our users say it has a similar feel to AutoCAD. But a lot of our drawing tools are made specifically with the MEMS community in mind. It contains a design rule checking tool called Tape Out. You're also able to visualize a cross-section of your structure using the layout visualization tool. And like most of the IntelliSuite tools, it works directly with our mesh engine. So here are just some images from Blueprint. On the left, we have a multi-layer design, and you can see all of the layers. You can view them transparently, so it's easy to work with them. You can easily work with arrays. Over there, the second image, we have a micromirror array. And that is one of the hands-on tutorials. We'll be creating an array using VB scripting. Then we have our cross-section visualization, and then an image from Hexpresso after we've meshed our layout. So here are just some more images from Hexpresso. In general, you have your layout information and then your layer processing information, which right within Blueprint, you're able to define all of the thicknesses of each layer. And then from there, when you mesh the structure, it will appear with those defined thicknesses. So just again, Hexpresso, it lets you click with one mesh. So you're able to just use your layout file, set a mesh size, and then mesh. You're also able to specify certain areas if you need a refined mesh in certain areas of interest. Next, here are just some more images from our cross-section viewer. With this, we're able to export either a sequence of images, a PowerPoint file, outlining each step with all of the thickness information. We're also able to export a movie. And this is something that you'll find in a lot of the IntelliSuite tools, especially the process flow visualizers. Next we have tape out, and this is our design rule check tool. So on the right we'll have a list of errors. So it groups them by error type, and then you can go back and easily correct them. It will flag them all for you. In general, you can create a design rule deck, which will just be your list of design rules either set forth by your manufacturer or what have you. And from there, as you're building up your layout, you can run the check periodically, and it will show you when these errors occur so you can fix them. So just a few examples. You can set errors based on intersection or angle-based errors, any sort of overlap that you're looking to avoid. And then with this design rule deck, you're also able to use it with as many blueprint files as you want. So when you run the design rule check, it will ask you for the deck file, which will have all of your rules. We also have several tools, several drawing tools that are useful for MEMS. These are just a few examples. Fillet and layer merge tool. Later in the presentation, I'll be talking more about IntelliSuite 8.8, our newest version. And that's where we've created a lot more blueprint features, especially merging tools and image import tools. So I'll have more about that later. All right. So that is what I have for blueprint. Next, the first tool that I wanted to go in depth about is Simple, which is our behavioral analysis module. Just a little overview. Simple is schematic based, so you'll have a schematic and then a library of elements that you can drag and drop and then connect them. Each element will have certain parameters where you can set values, whether it be for dimension or material information. This tool will work directly with Blueprint in that once you build up your schematic, you can automatically create a mask or a 3D structure and even a meshed structure. And from there, once you create the mesh, you can easily go to one of the multiphysics tools. And as I mentioned before, EDA Linker, it is a tool meant to help you bridge the gap between IntelliSuite and some other tools that you might use for whether they're circuit tools or just other analysis tools. So I'll go a little bit more into that later. That kind of involves both TEM and Simple. I have a little more information on that. These are just some examples of some elements that you would find in the Simple library. So anything from the small elements, the atomic ones, then more compound elements, and then device elements like this Resonator here. When you double click each element, you'll see a list of values that you can change. We include an element guide which has every single simple element in it and then explains what each value is and why you would want to change it, common applications for certain elements. So generally when you synthesize a mask directly from Simple, you might not automatically have exactly what you're looking for, but after tweaking it a little bit in the schematic layout, it's generally pretty easy to go from Simple to Blueprint and have a solid working layout that you can use later on for further simulation. So here we can perform certain types of simulation. It's very light. Right from within Simple, and we can view our results either in one of the IntelliSuite graphing tools or in Excel. So this is just an example of a bandpass filter that we've created using Simple. From here, we're able to perform analysis, and normally we would choose one node of interest where we will view our results. In this case, you can define all nodes as nodes of interest, and then it will create a 3D visualization. And like with the other tools, you can export this as a movie or a sequence of images for each frame.
When you say results, then what do you mean?
So depending on what you're looking for. So after you run, let's say, a dynamic simulation, and you want to see, for a gyroscope, let's say you have one node of interest and you want to see the Z displacement. After you run the simulation, in your simulation settings in the beginning, it will give you a list of things that you want your output to be, so you can select what they are. And then after your simulation, it will show a list of your outputs, and you just double-click the one you want, and it will show you a graph, whether it be with respect to time or whatever you define in the beginning. So this just takes it a step further, because instead of having one node that you're looking at everything to get a visualization. And then along with this, it will give you a larger data set where it will have different areas of the schematic and treat them all as different nodes. So if you have a certain area that you're focusing on, but you don't know what it is yet, this is a good way to see which areas of your design are doing interesting things, so you can look at them further. This is just an example of what we get when we synthesize a mask from our schematic. And we're able to set very particular details. So when you when you click on certain elements, it will give you these options to add dimples or add some sort of effects like etch compensation features, things that could be useful when you eventually go to fabricate your device. And then from here, using a tool called Quick 3D, we can easily build up a 3D model. And this 3D model will be compatible with, we're able to export a couple of different file types. So we have all of our IntelliSuite file types, and then we also support IGS and a few others. I believe IGS is compatible with SolidWorks and Pro-E. So I know some of our users have been using Quick 3D, where they will just resave it as an IGS file and then bring it into SolidWorks to produce their technical drawings and everything. And then once we have this 3D model, we're able to immediately mesh the structure. It doesn't actually require that many steps, so we don't have to have the mask and then the 3D model and then the mesh. In Simple, you'll see some buttons at the top where you can just say mesh and use this multiphysics tool, and it will open right within that tool. Next, just a little bit about EDA Linker. Sometimes you'll want to take a file from your multiphysics tool like TEM and incorporate it into Simple to see how it would act as part of a system, or yes, to say you have a mirror array, you can bring the single mirror file, your reduced order macro model, into Simple, and we have a macro model template where you would import all of the associated files. From there, you can run simulations using that tool, using Simple, or if you're using a different tool, you would just run it through EDA Linker, and it will create new files that are compatible with that EDA tool. So just the main benefits of Simple. I'd say the biggest one is just that it is faster. It's much faster than any sort of multiphysics simulation. It's useful depending on what your goal is. If you're looking for very accurate results, you would probably want to go with the FEA tool. But it's definitely a good starting point in the beginning of your R&D phase of creating your device. And Simple is one of our tools that works the best with all of the other IntelliSuite tools. So it's linked with Blueprint, Mesh Manipulator, TEM, IntelliFab. In some regards, you can generate a simplified process flow automatically through it. Next, we have our fast field multiphysics tools. Just an overview. They're fully coupled, so we cover, in TEM, we look at thermal, electrostatic, and mechanical components. For these, we rely on the Abacus engine, and then we've added in some additional IntelliSense code, and we combine all this to get better results. In our most recent version, we added some capability to simulate magnetostrictive devices. We also have two specialized engines, one called microfluidics, and it's for microfluidics and biomems, and then another called EMAG analysis, and it's for electromagnetic applications. And all of these work well with each other, so you can export a file to go to any of the tools fairly easily. And then this extraction part is just talking about how you can extract your macro model and then bring it into either Simple or into EDA Linker.
MEMS can do 3D analysis or not?
What is that?
MEMS. Last time I was trying to make a 3D model. It was impossible.
I mean, it's...
It was generally speaking a 2D module, not a 3D module.
for the most part, it is just looking at a 2D part, whether you're doing electrowetting or a chemical reaction or anything. It will give you a 2D view, and then if you go to and post-process it, it doesn't open in Visualise, which is our regular visualization tool. It has its own. It will show you some 3D features to a certain extent, and then you can choose whether you want to see the vectors or the just some images from it. I have some slides later on it. But it is not the same. It's a similar interface to TEM, but it's not, when you're setting up your simulation, it won't, you can't rotate it and everything. You need to look at it 2D originally. I hope that helps. I don't know. It's something in the example guide. I know there are a few that involve 3D models, and then if you bring in your 3D model from TEM, it should show up. But I know there are some limitations going to the microfluidics tool. So here we just try to use the best solvers for each of the physics domains and then bring it all together at the end. So by using these different methods and using our meshing tool, we're able to get fairly quick results. I know FEA simulation is sometimes very slow, but we've compared it with some other tools in the past, and using the meshing methods that we're using and coupling that with using the different solvers for the varying domains, we're able to get quick and accurate results. So here are just some examples of things we can do in TEM. Here we have, we perform a contact analysis where we have these two beams making contact at several points. And we're able to choose our nodes of interest and see as we are closing the two beams upon each other, seeing the displacement, and we can see at the top where the contact is made. We also take into account Seebeck effects and other effects that are common in MEMS devices. So here we have a view of some simulation results for the temperature and the Seebeck potential for this particular device. Next, one of our newer features, we released it in the last build of 8.7, and now it's completely part of 8.8, is this magnetostrictive material analysis capability. So one of the demos that I'll be giving is of a switch device that relies on these principles, where we will apply a magnetic field and then see it actuate. And then for the fluidics tool, here's just some examples from there. So in the mixer at the top, that is what I meant. Once you post-process it and view the visualization, it should show you a 3D model depending on your simulation. It's definitely something, if you're looking to perform a certain type of analysis and something's not working right, our support team should be able to help. Oh, it's actually in the next slide. So here we have a fluid structure interaction. This example we actually use TEM for because TEM does have some fluid structure interaction capability. I have an example right here. So here we have a micro pump. And we apply a voltage and a 0 voltage there. And here in Visualise, we're able to see what's happening. If we were to rotate it, it would be 3D. In this view, we haven't done it, though. This is probably one of the more complex simulations that you could run in TEM. We include an application note and all of the training files for it. But if you're looking to create a different type of pump, it could get complicated, but we're always looking to create better documentation to deal with that. So these are just some examples of things you can perform using the microfluidics tool. So certain types of chemical reactions, and then we look at transport behavior. Electrowetting on dielectric, or EWOD. And this will use Visualise, so once you run your simulation, you can see a movie of the droplets moving around the track. Here's just an example of what a movie would look like from Visualise. This is an electrophoresis example. All right. So now I have a few demos. One for a magnetostrictive device. This will use TEM. And then the following one will be for a Tang resonator using Simple. So here we have our magnetostrictive switch. I turned the mesh off because the mesh is the same color as the background. But here we have our beams that will deform when we have a magnetic field present. And then here we have a small gap. And this will make contact here and complete the circuit. This gap is 5 microns, I believe. And once we have a certain strength of magnetic field, the beams will cause this to actuate upward. So the first thing we would do in TEM once we have our model would be to set our simulation settings. So here we'll be running a static simulation for magnetostriction as the analysis type, history result, and one of the most important parts is we want to make sure that this box is checked for contact analysis, because these two parts will make contact. Oops. The next thing we'll want to do is take a look at our material information, especially for the beams. So we go to Material, Check, and then select the entity. So here we're able to either import a material from MEM material, or we can just go in here and change any values that need to be changed based on the material we're working with. So here we have our electromagnetic parameters that will come into account for this particular simulation.
Do we need define contact elements or?
Yes, we will. In this example, we actually do that last. But you can do anything in any order, and it will generally work. Next, we set our loads and our static magnetic field. Well, that is our load. So first, we just click magnetic field, and then our beam element. I actually already have it defined here. Oh, it opened on my other screen. So here we're setting 30,000, and that's in the X direction. And next we need to set some boundary conditions. So our anchors here and here, we'll just set a fixed boundary condition for each. And then this part, when they make contact, we won't want it to move. So they've already been defined in this file, which is why they are showing up. A lot of them are duplicates, though. Next, we need to set the contact part. Let me turn the mesh back on. It might give an easier view. Yeah. So we want this face to make contact with the face underneath here. So in order to do this, we go to Boundary, Contact, and then Face Pair Definition. And we can set face A as this one. And then we'll need to set face B as this over here. And in this case, it would be deformable. That is incorrect. I'm just going to do it again quickly. Well, I deleted things too many times. I have a, well, once we do that, once we set our contact pairs, we would then need to complete the pair and just select A and B again. and then verify our contact pairs, and it would give you a window showing the two pairs or the two faces that would be paired. I don't know what I've done here to ruin it. And then that would be our last step, and we would perform our static analysis. And once we do that, we would set our increment number, which in this case would be 10. This simulation would take about an hour to run.
How many elements do you have? How many elements do you have for this simulation?
Well, we used 10 increments, but the only elements that we're looking at in it are the switch component and the beams. The only entities. And then we view the results. And these would show up directly within TEM with the color scale. And here we can see that it's making contact when we use that magnetic field. We can also look at the stress and deformation, closer look. Next, if we want to perform a dynamic analysis, we can do that as well. We would just set the simulation type as dynamic, and then here we set an amplitude curve. And then from there, we're able to choose a node. In this case, we chose the part of the switch that is moving. So something on that face, and then we view the displacement versus time, and here's where it's making contact once it moves 5 microns. Does anyone have any questions so far? All right. The next example involves simple, and it will be to build a Tang resonator and then run some basic simulations using the behavioral analysis tool. All right. Here.
You mentioned about DEM, boundary element method. For electrostatic analysis, do we need to add air or between two electrodes, or because we are speaking, we are not going for final element we have, but for boundary element method, I was thinking for electrostatic analysis, maybe we don't really need to.
I think with electrostatic analysis, you wouldn't need that. If you did, it wouldn't be set as a load. It might be part of the when we looked at the magnetostrictive elements in the material properties window, it could have been something there.
We don't need to more than 2 electrodes, with no media inside those electrodes, because it's going to be a plus. If you are using boundary element method, it's going to be something.
So when you model something in TEM, typically it's treating the medium in the middle as a vacuum. If you want to have another sort of medium, you can set some global parameters to change the surroundings. But in a case like that, if you want to have a gas or something with certain properties, you can create another entity that just goes in between, and treat it as totally deformable, so don't set any sort of contact pairing with it. And that's how we would recommend to do that with TEM. For electromagnetic simulation, though, it would be different, and that would involve use of the other tool. And with that one, we take into account more of those values that you have to consider for the electrical simulation. So here we have our typical simple window. Here's our schematic on the right, and then our element library. Here we have everything. A lot of them seem pretty similar, especially if you're new using the tool. But we include several examples in the documentation, as well as the element library guide, which will explain each one and why you would need to use them. All right. So for this training example, we will use this Tang resonator. And the first thing we'll be doing is performing a basic frequency analysis. So first, just like in TEM, we'll need to set some simulation settings. So if we go to AC analysis, in this case we'll want a frequency sweep. So instead of just setting one, we'll set a range. And here we'll go, our starting value will be 1000 hertz, and our ending value will be 1 megahertz. And then the number of points that we consider in between, that's just our step value. In this window, we're also able to just define a table of values. So say you want to see a selection of frequencies not evenly spaced from each other, but just several values, you can just input them in the table at the bottom. And then here, this signals part, this would be where we would select our output component. In this place, we're just looking at Z. Let me see. So once we press OK, it will begin running the simulation. This one actually takes about a minute, I think, a minute to a minute and a half. Typically, your simulation times in simple will not be very much. If you're working with an array or any sort of much larger system, it's something that you'll notice that it takes a little bit longer, but it's nothing compared with the FEA simulation, which can sometimes take a lot longer. So now we can open our results in WaveRunner, which is one of our data viewing tools. So here's our WaveRunner window. So first, we'll need to import our data, which would be this one. And next, we will add a chart. So here we can see where our resonant frequency is. And with this tool, we're also able to change the way we view our data. We can look at a log scale, linear. A lot of our users will end up just exporting this data. So you can get a raw view here, where you can select all and then copy it either to Microsoft Excel or MATLAB or whatever you might be using. We've had some of our users simply copy this into a text file and then import it into MATLAB, and then they can graph things with that. Next, we can perform DC analysis. And in this case, we want to look at all nodes because we'll view it in the Visualize visualizer. All right. So here we have our view in Visualize. And we can see our same information just in a more graphical view. If you were to perform a dynamic analysis or a transient analysis and then look at all nodes and open in Visualize, you can actually have an animated movie.
For example, if you want to do electrostatic analysis right now, what is come to life?
Yeah.
How do you do that analysis?
For this particular one, we would use probably one of these settings, so the transient analysis. That simulation time takes longer than the AC and DC basic simulations, significantly longer, but still it would be a lot faster than any of the multiphysics tools. From there, though, once you're in Visualize, if I still have it open, it will give you anything that you selected as a signal before you ran the simulation. It will show you here. And then this gives you a lot of flexibility how you are looking to view it. If you're dealing with an electromagnetic application or microfluidic, the vectors could definitely come in handy. In this case, not so much. And then again, if you are running a simulation where you have certain increments and it's based on time, this will take each increment, take a snapshot of all the nodes, bring them into this tool, and then you'll be able to view them as more of a movie. All right. Are there any questions about the device simulation so far? I think I'm running a little ahead of schedule. I do have one more example using TEM. This one's just slides. This will give you a good idea of what some of the routes you can take are when you set up a basic tool flow, when you want to start out with your design and then run some simulations. So in this case, we have a VOA, a variable optical attenuator. This one is thermal, so when we apply a temperature, the beams over here will deform, causing this to move upward, and then we can control our optical signal that passes through. So with IntelliSuite, we usually have a few options how we want to get from our original design to simulation. So this will cover both of those. So we'll go from blueprint to create our 3D model and then go directly into our multiphysics tool. Or we can use blueprint and our process flow information to visualize our results using FabViewer. Then we can go to TEM from there, or directly from FabViewer. And you'll just see that the results are similar either way you go. So here's our basic layout and blueprint along with our material information. And in this case, we started out with a GDS file that we converted to .vec. So .vec and .msk are the two layout formulas that Blueprint uses, the two IntelliSuite formats. Most of our tools support both of them. If you're starting out with a GDS or a DXF file, all you'll need to do is open it in Blueprint and then just save it again. And it will become a .vec. Here we've used 3D Builder. 3D Builder is kind of like a mix between Blueprint and Hexpresso. So in this tool, you import your two-dimensional mask, whether it's multi-layer or not. And then on one side of the screen, it shows you your 2D version, and on the right side, it will show you a 3D model, and it's live updating. And in there, you're actually able to modify your mesh. So if you have a mesh structure already and you want to enhance a certain region or give a certain region a more refined mesh, if you decide not to use the auto meshing tool, which we would recommend, you can actually do it by hand in 3D Builder and define your own mesh area. From there, we bring it straight into TEM. Just more information about the material properties. And here we set a voltage of 0 at this node and then 3.5 over here. And both of these are fixed faces, so only the beam should be moving. Here we can see our temperature distribution and our displacement. So our displacement in the y direction, well, that would be how we're actuating our optical signal. You can see here that it's moving once you apply a voltage. One thing that is important to note in this particular example, if you change the beam of, if you change the angle of that beam even by the slightest amount, it can affect your results drastically. So we've tried adding a 1 degree difference in the beam angle, and then we run our simulation again, and we can see that we get different results. It's probably a little too small to read. I'd have to view the old results. It is remarkably different, though, going from having 0 degree and 1 degree angle in the beam. So it wasn't until about 2 weeks ago with IntelliSuite 8.8, we created this new Parametric Analysis tool where using VB scripting we would have to use, we would modify the layout, and then you set the parameter you want to change and then a set of values that you want to go through, and it will create all of the layouts, all of the 3D models, and then perform all of the multiphysics simulation. It happens one after another, so it takes a while, but it's unattended, so you can just go, and then it will show you, if you want to view the y displacement for all of them, in the end it will give you a result graph where it will show you what the angle difference was on one axis and then what your displacement was. So with that tool, we focused more on dimensional differences, so for a comb drive, the width of the fingers and how that affects certain things in it. But if you wanted to change an angle, it would just involve more scripting with the VB scripts. But chances are we have several templates. One of the live demos will be using one of them. And just from looking at them, you can kind of infer how it works. And if you need any additional assistance, we have a VB scripting guide that we wrote specifically for Blueprint.
Can we multi-factor of those devices somewhere inside the different modules?
Multi-factor. I'm thinking no. I might have to get back to you on that though. Especially not in the parametric analysis tool. Maybe somewhere in TEM. This is just, in this particular example, we're taking another route and using our process information instead. So here we just have some basic information about our process. And from this, we build up an IntelliFab file that we can view in the process flow management tool. Using this IntelliFab file, we can go either to FabViewer or directly to TEM. So in this case, when we view it with FabViewer, we'll get a representation of each process step. And we also have the option of going directly to TEM. It will run through Hexpresso. We'll set our mesh size. This looks different because in this case, we actually, if we go to the previous slide, we added a packaging around it. So we can see in this layout on the top left, we've added some packaging structure around it directly within Blueprint. So we'll see when we compare our results. The differences, and they are slightly due to the different ways that we've built up the file, that we've built up our 3D model. The rest of the difference is mostly through the packaging effects. One thing you'll notice if you use FabViewer, you really won't have much of a difference because it's just modeling. It's just a voxel-based simulator that's modeling the additive and subtractive surfaces, adding the layers and taking away certain features. If you use FabSim, which uses more physical-based algorithms, I'll get more into that later, you will have more accuracy when dealing with certain processes like wet etching. So in that case, you might see more differences, but in a good way because they're more accurate. All right. Are there any other questions before I move on to the process tools? All right. So one of the things IntelliSuite, one of the things that makes it unique is just that it contains not only the layout and device simulation tools, but we also include a collection of these process simulation tools that we call Cleanroom. So just a little overview of Cleanroom. We have IntelliFab on the left, where we would manage our process flow. Then we have our standalone tools, FabViewer, FabSim, Anise, Intella Etch, and Recipe. We have one more that's not listed called Exposure for lithography. All of these tools work directly with MEM material, our material database, and Hexpresso, which we worked with before. So this is just a basic overview of IntelliFab. It's popped up a few times already today, but this just gives an overview of the layout. So here we have our process flow. So each process step, all of these we've taken from our process database, which shows up on the left when you have nothing selected. From there, you can take some standard processes, drag them over, and then it will give you this parameter list where we can input our own values. From here, we're also able to go back to our blueprint layout without having to close everything and resave everything. It will just pause IntelliFab, let you change your layout, and then once you close blueprint, it re-imports the file. And then we can visualize with a few different tools or run an analysis with TEM or one of the other multiphysics tools. So this is what FabViewer will give you. So on the left, we have the same Tang Resonator design from before. And on the right, we have a micromirror design from TI. Obviously, it's scaled a lot in the Z direction. One of our newer tools, we came out with version 8.7, is called FabSim. So with this tool, when you do deep RIE or wet etching, you'll notice some differences in accuracy from FabViewer. So FabViewer is just a geometric tool that will, if you were to run a design like this in there, if you have a mask and then you do dry etch, you'll have all of these cavities will end up having the same depth because it's just removing the material in a standard way. This takes into account some of the phenomena that are present with these etching processes. So the lag effect would cause you to have these different depths for the different channel widths. Another example would be for wet etch. This is actually one of the hands-on demos. When you do corner compensation analysis, so when you have to modify your layout to get the corners to look the way you want, for this we would recommend using either Intella Etch, our etch tool, or FabSim because it uses a more advanced algorithm where it takes into account these effects. If you were to view this in FabViewer, you would have a useful result, but if you're trying to make detailed measurements, we would recommend using this tool. The simulation times are a little bit longer in this tool, but not by a very noticeable amount. One of the things we try to do with IntelliFab as well as Tape-Out, our design rule tool, we try to incorporate as many commercial design kits as we can. So here we have the multi-user MEMS process from MEMS Cap. In this particular case, I'm not sure which one this is. It might be SOI mumps. And when we take these, generally they will just give us their design the handbook where it contains every process step, all of the important information about it, as well as their design rules. And then we create a package that will contain the design rule deck, the fab file, and usually some sort of layout that we've created. And these are part of our free FabViewer tool, which can be downloaded on our website. We're working with a couple of these foundries where they will post a link to IntelliSuite along with all of the other MEMS tools on their website. And then you can download a free version of FabViewer as well as all of their process flow information, so you can plug in your own GDS mask and then go from there. You would need to buy IntelliSuite if you want to edit any of the process steps, but in general, a lot of people are just looking to use these processes as they are because you can fit more than one project on the wafer. So they save a lot of cost. From IntelliFab, we can also export a process traveler. It's basically an Excel spreadsheet that contains every piece of information about your process flow. So it's good for sharing information with colleagues or whoever is fabricating your device. This tool, FabViewer, FabSim, and the Blueprint cross-section viewer all can create these PowerPoint files where if you're looking at any particular cross-section or anything, it will just show you your current view, but for each process step. And then at the end, it will give you a summary of the processes used, the materials used, what all of the colors represent, and everything. And then from here, you can definitely edit these if you want to put them in some sort of different presentation. You can take the images out of it. One of our recent developments is exposure. It's a module we've created specifically for lithography processes. We can model exposure, post-exposure bake, and development. This is just an example. It uses your layout from Blueprint, and then we set all of our lithography properties. And then after running the simulation, we will get a view like we have on the top. And then from there, if we want to, we can even mesh that and use it with TEM. Next, we have Intella Etch. This is probably one of our most popular tools. It's an anisotropic etch simulator. We've recently released a GPU version that uses your graphics card to run simulations up to 100 times faster than our CPU version. When someone purchases Intella Etch, we just include both versions. We also include a calibration tool, which I have this first. We recently added quartz etching in version 8.7. So we have the ability now to simulate etching on silicon and quartz at several different wafer orientations. So you can either choose one of the standard wafer orientations or input your own during the definition phase. And this is what I was mentioning before. We include a tool for calibration for Intella Etch. So here we have this wagon wheel design where we would send the user our mask and they would run the fabrication process. It involves a couple of processes. It's a deep RIE step and then a wet etch. For different wafer orientations, then we take a look at it in our wagon wheel analyzer tool. And this extracts the etch rates and allows us to calibrate Intella Etch for their particular etchant. If they're working with a different etchant, different temperature, concentration, whatever, from there we can calibrate the tool more effectively. This is something that the users can do on their own, but it's something that our support team does all the time, so we don't mind doing it for them once we get the SEM images from their fabricated sample. Next we have Recipe. This is, there are two versions, Recipe 2D and Recipe 3D for dry etch analysis. Here are just some comparisons with experimental results. Here we have a few more. This tool works a lot like FabViewer, so you'll notice a lot of the same viewing and measurement tools, especially the way that you can deal with cross sections. So here's the 3D version. You'll see here we look at a cross section to see the inner cavity of the structure. Okay. Next, from these tools, from IntelliFab and some of the standalone tools, we're able to output a usable FEA file, which we can then export to a variety of CAD formats as well. Here's just an example of that same micromirror array that we had earlier. On the left we have our view from FabViewer, and then on the right we have the mesh structure after running it through Hexpresso using our process information. All Now I have two demo examples. First, the metal mumps process flow. This is one of the ones we've received from MEMS Cap. So when we open IntelliFab, okay. So as I mentioned before, here we have our database. And then if there's a certain process you can't find, if it's similar to another process, we can generally modify them to add them to the database. Our support team can implement them fairly quickly. If it's something completely new and different, it could take a little longer to implement, but we usually do our best to add things to the database based on user request. So if you're ever looking for anything and you can't find it, just let us know. All right. So first we'll open our process flow. In this case, it's in the training folder, Fab Viewer. So here, if we just look at all files, as I mentioned before, this contains the mask files in a few formats, the Fab file, as well as the design rule check file. So here, it will look in the same directory for a mask with the same name. So here we have it, and we select the area that we want to look at. And here, when you select individual processes, it will show you everything that you're able to change. And in this case, we've grouped some of them just to make it easier to view. Okay. Next, we can visualize in FabSim. Okay. In this case, I'm going to do a low resolution one because I'm on my laptop. And these are the cross-section tools. So this is how you would view a cross-section. In this case, we can view one halfway in between just to see. Okay. And then, is it in the way? So here we have 49 steps. You'll notice in FabSim that the deposition and lithography processes are pretty straightforward and quick. Where you run into a little bit of simulation time is with some of the etch steps will take a little bit longer than others. And that's because it's using a similar algorithm as our standalone tools like Intella Etch or Recipe. There's still two more. There we go. And then you'll get a little bit better of a view with a higher resolution. So here we're able to, there are a few other tools we're able to use. Here we have a layer extraction tool. I have more about that later I can show. Right within FabSim, you can also view your process table. So if you're interested in looking at this deposition step, you can go down and see more about it here. And the output pane, just for if you run into any problems. And then, like most of our tools, we have basic measurement tools for X, Y, and Z measurement. All And as I mentioned before, you can export in any of these ways, whether it's PowerPoint, a video, image sequence. And then from here, we're able to go into TEM, Fab Viewer, or Mesh Manipulator if we want to just create a CAD file, and even just directly back to Blueprint. Next, I have an example using Intella Etch. In this case, we'll use Intella Etch G, the GPU module. So the first step in Intella Etch is to define our sample. So in this case, we use 100, 100. Our sample will have 4,000 microns in the X direction, 4,000 in the Y. This is basically a resolution number, which shows the method that Intella Etch uses is a cellular automaton method, where it's actually looking at the atomic bonds for each atom and deciding which ones will be stripped away during the process. So in this case, our default value for this is 256. It's just the nodes of concentration. So I'll just leave it at that. In this case, I will set a thickness of 190 microns. And here we have our sample. All right, so first we will apply a nitride mask to the top. So this particular tool, the mask tool within Intella Etch, supports BMP image files as well as the .msk IntelliSuite files. Oops, I'm in the wrong folder. In this case, we are setting nitride and applying to the top. So when we do that, our mask will appear in red. Here I'll set a different transparency just for easier viewing. And we'll also be applying a nitride layer to the bottom. So this applies it to our bottom layer. Then we'll run our first etch step, wet etching. And we'll want to use one of our etchants from the database. So in this case, KOH. 40 concentration at 70 degrees C. And for this initial step, we will do it for 80 minutes. And depending on how fast you want your simulation to run, I think it's good to show the animations sometimes. That will make it a little slower, but you'll see the real simulation speed of the GPU version is very quick. I have the window over here. So without the animated view, it's probably about 3/4 of the speed. All right, and now we take our masks off. From the top and the bottom. And we're left with this here. Next, we'll apply a nitride layer again and perform another set of etch steps to get our final design. We're making a micro probe in this case. So we can apply this to the top. And to the bottom, we're just going to use the same complete covering as before. And all etch times in Intella Etch are cumulative. So you'll notice it still says 30 here. So no, it's supposed to be 80. What does it say? Well, anyways, whatever time you type in here will be the total time. So if you want to perform an additional 100 minutes, you just add 100 to your time. So in this case, we want the total to be 350. To make it a little faster, I'll do non-animated or maybe checkpoint animated. And the same etchant as before. And lastly, we just need to remove our masks and get our final result.
Can we export this as a 3D image somehow?
So what we can do with it is export it, but it passes through our mesh engine. So your 3D structure will be a little bit block-like. It's still usable in our multiphysics tool, but something that our team is currently working on is extracting more of a pure geometric file almost based on the point cloud that this generates. So if we zoom in very close, we'll see that it's a cloud of points.
Yeah.
So just connecting those in a reasonable manner and then exporting them into a usable CAD file. The current version can do it, but with some limitations. Generally, some of the export features here that are available now, obviously images. So this IntelliSense FEM mesh, that will give you a .save file which you can open in TEM.
It takes forever. I tried once.
If you set the resolution higher than 100, it takes a long time to open, and then once it's open, it's just very taxing on the machine. So that's something we're currently working on now. This XYZ coordinate export method, when you export that, it gives you a file, and then you can import that into Mesh Manipulator as a point cloud format, and then save it as IGS or an IntelliSuite 3D model. But certain, we've noticed some strange limitations with that feature right now. So it's something that we're currently developing and hoping to get out in one of the first 8.8 releases after the original one. One of the most common questions we get whenever we show someone Intella Etch is whether you can do the opposite, whether you can start with something like this, something like the model we have in the end, and then determine what type of mask we need based on what etchant we're using and the times and everything. And at this point, we can't. We just go one way. But still, it saves a lot of time and money being able to cut out an iteration during your research phase when you're fabricating things. If you can run some simulations first to determine what your final structure will look like, it's certainly useful. In here, we can also perform measurements. just like with the other tools. It's showing up a little strange on the screen. Say we want to measure X. Measure something here. Measure distance. And we just set 2 points. It will give us X, Y, Z, and then the total distance from point to point. So the newest feature in Intella Etch is definitely the GPU enhancements and then the ability to simulate quartz etching. And then for that particular example, we have an experimental image here. So you can see that they line up pretty well. All right. Let's see what's next. Next, I see a break before the hands-on tutorials. I think we're running about 10 minutes early. You can see. So just an overview of what we'll be doing for the hands-on tutorials. First, we'll be creating a comb drive using Blueprint from scratch using the drawing tools. And for that, we'll basically be using mostly the rectangle tool and then some of the manipulation tools like the mirror tool to copy your design, make it symmetrical. Once we do that, we will create a block from it and then use the VB scripting to create an array of the comb drives. Next, we'll do the corner compensation example with FabSim. That's only 2 process steps, so if you want to work with a different file, that should be fine too. There are tons in the training folder. I just think that's a pretty good example to open that design in FabViewer and in FabSim and notice the differences. And then the last one will just be working with the 2D layout and the 3D model formats and converting them back and forth a couple of different ways. And then with that, we'll take a look at a few larger files using Blueprint. And then this machine is not able to do it, but once we do that, I have some images of what the 3D structures look like. It requires a lot of RAM, and that's something our team is also working to make the 3D model generation just in general a little bit more efficient, so we can start doing more wafer-based things and more complex designs. And just a note, it's also written there, the documentation files are in this directory. So all of the hands-on tutorials have a documentation file that goes with it, so just instructions that will go along with what I'm doing. And they're all in this handout as well. It shows the particular file. All right, are there any questions? All right. All right. Does anyone want a break, or should I just continue with the hands-on? All right. So first, we have this comb drive creation with Blueprint. Does anyone need help finding the instruction file, or it's there? Okay. So when we open Blueprint, first we just need to create our new file, and by default this gives us a .vec file. And first we'll create our outer figure by specifying our corner coordinates. Oh, my caps lock is on. Here we can see the first rectangle we've created. Next, we just create a few more. So here we can see the outer structure. Should be symmetrical. All right. Next we create an anchor, which will just be another rectangle. So we have 75. These can also be made by simply dragging from one point to another, and you're able to control the grid and snap settings to show where your mouse will stop. In this case, I find it easier to just type in the coordinates if you have them on hand. All right, -65. Okay. And then if we wanted to, we could join all of these using Pathfinder, which is the layer management tool. So if we select all, we can create a union, and it will join these parts. In this case, we don't need to do that. Undo it. There's actually one more rectangle, and something's missing. There we go. All right, and next we'll want this to be symmetrical. So we will mirror it over the y-axis. So here, using the mirror tool, we select all of the objects that we want to copy. Use mirror, and right along the y-axis will be our axis of symmetry. this off. Okay. All right, then our next thing will be to create the center figures. So in this case, I'll also just use the rectangle command. Oh. Wow. Okay. I have the wrong tool selected. Okay. Rectangle. And then to create each comb finger would certainly take a while. So in this case, we're going to just create one and then create a block from it, which will, and then once we insert the block, we'll create a linear array from that. So these will support the fingers here.
What's the difference between the blueprint and the mask module in the software? Because we can do the same thing. We can draw the
I mean, in this case, we're just building up the design from scratch using using rectangles in Blueprint, and then
you can do the same if you open the mask.
I'm saying if we didn't have the mask available already. This is how we created the mask.
But you can draw that on that module as well. You can do the same thing.
Which module? With the schematic module?
Mask module.
IntelliMask?
Yeah.
Oh, okay, so IntelliMask is essentially the same thing as Blueprint. They're both just layout editing tools. And Blueprint is eventually going to replace IntelliMask in the future. We created the separate file format. The .vec file holds a little more information than the .msk from IntelliMask. But what we've tried to do is create, take in all of the features of IntelliMask and just add in the ability to view the cross-section and just more compatibility with the other tools. So you're absolutely right. In this tool, if you view the filled layers, it just has a different look and feel than IntelliMask, but a lot of the same features are here. But in this case, all you need to do is the last step is to just create the fingers and then insert them as an array using the block function. I did that incorrectly. Rectangle. So we'll create both the top and bottom fingers. Actually, that's just creating the original one. So here, if we zoom in on the finger, select it, and then right-click, we can create a block. We'll name it comb finger. The block window is here. Next, we can delete the original one and then insert it somewhere in our design. So in this case, the insertion point will be right where the first one actually is. So that deleted it, but it created our block. So next we'll just insert the block. And our insertion point will be the location of the original one. -36. No scale. And we'll want to create several of them. So 15 separated by 5 microns in this case. So we have that, and then to create the top, instead of drawing the additional rectangle, we can just insert the block again. And we just set a different starting point, and it's exactly the same. So maybe 36. And we'll have 14 because they'll be on the inside. You can probably get a better view of the little layers. We'll just save this. Next, with Blueprint, say you wanted to have a bunch of these, and you could just create a block of the entire element, or select everything and use the array function. But if we want to combine it with other elements, we can also use the scripting tool. So in this case, if we open the script editor, we can open one of our pre-built layout scripts. In this case, it is this linear comb drive element. So here it gives you an explanation of what all of these variables are that you can change. And in this case, we're just leaving everything the same. So here we can see our insertion point. And all of this is explained in the scripting guide. But in general, if you're working with, once you look at one or two script files, you'll notice some similarities and see, you can generally infer what is going on with most of it. So the values that you would want to change. So if we run this, this is not the same as our previous comb drive, but it is similar. So this bottom set of comb fingers, that's the rotor. So that'll be the part that's moving. This is the stationary part. Next, we want to add a suspension element, and we have a separate script for this. It is a passive element, and it is the crab leg suspension element. And again, we'll leave everything at its default value. So we can see here that it puts it at its default value. It's in the wrong spot. Okay. So if we delete it, and that's where the scripting would come in. So if we were to select it again, we can change some of the dimensions. So the length of the first beam, it's really just creating the same thing. It's basically like how we generated the comb drive before, step by step, making different rectangles, but it's just doing it in a script more quickly. So here, after measuring everything, we have new values that we can put in. It's a little bit tedious, but once you create a script and it's working for you, you can certainly save it and use it again later. Okay. And our start point will be 140 and 155. Originally it was at the origin. Okay. Well, it looks like I got one or two numbers wrong on that for the starting location. Wrong information, but in any case, what our end goal is, so that would have connected right down here. Yes, I could. The sizing is a little bit off as well. But this is the basic idea of what it would look like. Some excess elements here. Now, if we save this as now we can also create a block from an entire file. So in this case, we can create a block. Blocks. We have this window. We can insert, add for file. And then we insert 0. So our insertion point will be 0, 0, 0. Scale is 0. If we want to create an array of 10 by 20, we can do that pretty easily. So really there's a few ways to do it. You can either create your block by hand or using any of the drawing tools. You can do it with the scripting. And then if you create a block, you're able to easily make an array of either a whole file or a certain element. Next, I just have that basic example using the corner compensation example. So here, if I open IntelliFab, wrong screen. So here we have our mask where we've added this element to get a better corner. And just a little background behind this. Let's say you use a mask like this on the left, and then you try to create, you run a simulation. You're not going to get those corners the way that you want them if you want them to be perfect corners. So what you have to do is extend the corner outward by a little bit, and this will make for a better corner in your fabricated sample. So these are images from Anise, which is our another one of our etching tools. It's the one that came before Intella Etch. We still include it as part of the clean room package. Some users find it very useful, especially for these corner compensation examples. And a lot of the etchants and documentation that comes with it are still very useful. So here we have a very basic process flow. And we can visualize in FabViewer. Okay. Try to get them both on here. And in FabSim, so to get a better view, we can use the cross-section tool just to get rid of this mask, or actually a better way, we can use this layer tool to, oh, it's just extending it. We have to move both parts. Just use the cross-section. So this just gives you an idea of what it looks like with FabViewer. So you can see that it doesn't really take into account what's going on underneath the mask once it gets to a certain depth. With FabSim, you'll notice a little bit of a different result. And as I mentioned earlier, since it's using a physical algorithm for these etch simulations, the etching process steps of each process flow will take the longest in FabSim, but the accuracy is unparalleled when you consider it next to any other voxel-based geometric tool. So there we go. So here we're able to see the differences. And one thing I'll mention is that in any of these tools, once you run it once, it will keep the information and it will just run very quickly from then on. And then when you export your movie, you won't need to run it all again. Lastly, I have an example where we work with the Tang Resonator file, using it with Blueprint, and then Mesh Manipulator, and then we go back from 3D to 2D. So first, in Blueprint, we can open our layout file. It's in training. blueprint. So in this case, if we use the GDS file, you can see here either with the layers filled or without. If we were to just use the quick 3D option, which is here, that would open it quickly in Mesh Manipulator. But the only problem that we have is that the layer information is not inputted yet. So in this case, we would just need to set the thicknesses and elevations for all of these layers. So here you can see all of your layer information, and this will travel with the file once you generate the .vec file from it. So this is ground plane 1, 0. Okay. Here we just have and really all this does, when you're converting it to a CAD file, it's just telling it what your thicknesses will be for each layer. I know in the documentation guide it also defines the process type as well as gives each layer a name. I think if we're just making a CAD file, we should be okay. All right. Since it's GDS, to work with Mesh Manipulator, it's just going to ask us to save it again. And once we do this, it should generate the 3D model. Well, first, it shows us this, which is what it's using. So here's our information. You can select and deselect certain layers if you don't want them. And it will open the model in Mesh Manipulator, and let's say we want an IGS. Here we have it. More of a Z-scale. If we were viewing it as a VEC, we'd be able to select and deselect the individual layers a little bit easier. But in here we can import all of these file types and then export to a handful of common CAD formats. Another method we could use, or actually in this same area, what we could do is work with a much larger file. So as I mentioned before, let's say we have something like this, and we open it in Blueprint. Opening it shouldn't be a problem. It's pretty quick to open large files, and you can zoom around and manipulate things, make any changes you need to make. The part where it becomes more necessary to have a good PC is when you generate these 3D models from it. So here for this example, we set this layer information again, and we've created a series of This is just panning around on Mesh Manipulator. And this is something that we are trying to make more efficient so that you can do it on any machine. I know this we did on one of the computers at our office. I think it took 9 gigs of RAM or something. I've tried it on this laptop before. This has 8, and it's worked, but it just takes a pretty long time. And then when you go to convert the format, it just takes a while, but it works. So it's something that we're always looking to improve, just the efficiency of how we handle these 3D models, and then finding good ways to convert them back to layouts if that's what we decide to do. So next, another good way to create a 3D model would be to use our process information. So if we were to open the fab file that we have available for that in IntelliFab, okay. We can visualize it in one of the tools, or if we go to visualize in Mesh Manipulator, it'll be the same deal. We haven't set the thicknesses, but the thicknesses here are available because of the process information. So when we set the deposition or an etch depth or anything, it's all incorporated in there, not in the layout file. And then in this case, we could do the same thing and do IGS. Doing it this way, because of all of the considerations it takes into effect from your process, especially the etch steps, this takes 20 minutes, so I'm not going to do it right now. But you'll get a result very similar to the quick 3D from Blueprint, just a little bit more definition, I'd say. So with Blueprint, you can only have a model where you'll have layers stacked on top of one another, and then if you set a sidewall angle, it will take that into account. But with this, it will give you a more realistic result. And then from there, you're able to go to your Multiphysics tool or convert it for another CAD tool. Next, well, the last thing actually, is if we want to go from a 3D model back to a 2D layout, we can use our tool 3D Builder. As I mentioned before, on the left it will show your 2D layout and all of your layer information down here, and then on the right it will have your 3D model. So first, to create this 3D model, we're going to use this Auto Mesh tool just to import that mask from before. If we already had the 3D model generated, that would work as well. So Blueprint. All right, and we choose our meshing engine. Okay, so this just shows one layer at a time. And then here we have our 3D model. So what we can do from here, we can either export for 3D or for FEA analysis using any of the, well, first we have to save. When you export with 3D Builder, it gives you some options. So TEM, or the TEM preprocessor, which that option is that's an old option, microfluidic or the electromagnetic tool. But in our case, we're looking to go back to a 2D layout. So if we export to Blueprint, version 2, 3D Builder will close, and we'll be left with this layout file. And you'll notice that since it meshed our model going into 3D Builder, all of the mesh is still there, and that if we want to get rid of that, so you wouldn't notice if you had the layers filled, it would look normal, but without them, it's still there. So what we can do is use Pathfinder. And then we will merge the layers. I'm in the wrong menu. Layer merge and the entire hierarchy, and it will get rid of all of that. And then again, if we want to go back again, we can set our layer information, etc. But now we're left with the same file as we had before. It's .vec, but we could easily export it back to GDS. All right. Are there any questions about any of the tutorials?
In general speaking, you are not going to use IntelliMask anymore. Because you are speaking, you are skipping that IntelliMask all the time.
Yeah. Yeah, I mean, in general, IntelliMask and Anise are two of the tools that we effectively tried to phase out by creating Blueprint and Intella Etch. But a lot of our users really like both of those tools, so they've stuck around. We have limited support for them. If anyone has any questions about them, we can answer them, provide them with more documentation. But when we develop new features, it will be in Blueprint and Intella Etch from here on out. But we will keep those tools and make sure they're compatible with everything for a while. We did have IntelliMask Pro briefly, but that was more short-lived. It was kind of like a mix between IntelliMask and Blueprint, and we decided to just take it a few steps further, create Blueprint, and get rid of the middle one. All right. The last thing I have is just a preview of IntelliSuite 8.8. We released it actually I think 2 weeks ago at MEMS 2014 in San Francisco, where we basically showed these slides. And we're rolling it out slowly with most of our users. We're starting with the universities. So every module, almost every IntelliSuite module has been updated in some way. We've also added a completely new module called Parametric Designer. These are some images from that. So first, we updated Blueprint. A lot of these features exist already, but we've made them a little more user-friendly. Some of them are completely new, though. So just this layer merge feature, we've enhanced the Pathfinder tool just to make it easier to navigate. A lot of these functions have very similar names because they do very similar things, but they have subtle differences. So we've tried to make it a little easier to navigate. This fillet feature, we've added a feature to recover a corner if you need to. So it will look at the radius and then recover the corner. We're able to simplify entities a little better. So here we have a spiral, and we've simplified it by creating a number of lines. And we can specify a certain tolerance, and that will tell you how much it's simplified. This de-embed feature got a little bit easier to use. It's based on a set of Boolean operations, and we can remove entities that are embedded in other ones. This split feature, we're able to split a polygon by drawing a line through it. So once you create this line, it will just create a boundary on the edge and create the separate entities. The polar array and matrix array, that's been around. One new feature we've added is in the matrix array, we can add our own labeling method. So say you want it to say C1, C2, R1, R2 going down, you can define how you want your labeling scheme to work and it will go from there. The newest feature, probably the biggest improvement, is this image import function. So this is something where you would import an image of any of these formats, and then we set a tolerance and a simplification level, as well as a detail value. It's in, once you download IntelliSuite 8.8, we include a guide that explains each of the new features. So this is the one that has the real guide. And we include a couple of images that work well with it. But really, anything, if you import an image, we give some documentation on what each of the, when you specify the tolerance and the detail value, what they mean, and then when you have something like the one on the left, if you don't want all of those features in the middle, how you can eliminate them easily, or how to not get them in the first place by using different tolerance. And then just the Pathfinder tool, we've improved it a little bit. So here we just have some basic geometrical operations. So here we create a separate set of entities from the overlapping parts of the one on the left. All right. And then we have the same over here. We can create layers using any of these features. So if things are inside one another, if something overlaps, we're able to create a separate layer from that entity. We can create layers based on the area of each of the entities. So we set a particular range and it will create one layer, and then we continue by setting different ranges for the different layers. And also by density. Of the inner feature. So here we set an area ratio 20 to 25, and that will be, you can see here 14%, so the logo is smaller in each one. So we create these layers for ratios outside of that range, and then anything that's in between 20 and 25 will be that will be the green layer. I think this is outlined in the brochure a little bit nicer. Next, some enhancements we've made mainly with the mesh engine. So with 3D Builder, we enhanced the auto remesh feature. So the one that we used, auto mesh, there's also auto remesh. So once you already have it meshed, you can create a, say you set a minimum mesh size, it will remesh it using that. But if you want to do it for just a certain area, you can do that, and instead of remeshing everything and taking a while, it will just remesh the area that you've specified.
And I understand that 3D Builder cannot create shared surfaces, for example, like hemisphere or anything like that.
I mean, that's something we have improved in 8.7. I have, it's not in this presentation, but I have some good images of hemispheres that we've meshed. Definitely for more features like that, we would probably rely more on Hexpresso, just because it's our updated engine. But with 3D Builder, we're able to do a lot more than we could in some of the previous versions. Here's just a little more about the refined mesh. One of the biggest improvements, we created a 64-bit version. So most of our tools have a 32-bit or 64-bit version. Hexpresso was not one of them. So now we have the 64-bit one. We can handle larger and more complex models. We can refine areas a lot more, set multiple areas for refinement as well. Here's just an example of sidewall angle mesh. And just some examples of mesh manipulator versus the meshed view using Hexpresso. As far as process simulation goes, we've made a few enhancements for FabSim, higher index surface etching. So this is something that we've had in Intella Etch, but we've improved for FabSim. This is just an example from Intella Etch. Here's more about quartz etching. So this isn't really new, this is just more views of it. But what is new is these calibration tools that we've created. So this is a new one for recipe for DeepRIE. So originally we had where you could just input all of your values, and then using those and using your etchant information, it will go from there. But now we're able to import some calibration data, and the software will consider that as it performs its calculations. It's something that we already had in Intella Etch, but not in recipe. With Intella Etch, we've improved the wagon wheel analyzer to include 4 cuts instead of just 3. And with this, we're able to get much more accurate results. This has come about mainly, we've had a lot of users coming to us trying to simulate quartz etching. And we found that using this method with these 4 cuts, we get the most accurate results. So we've improved the tool to include all 4 of them. With device simulation, magnetostriction analysis, this is the example that I went over before. We also include a application note for magnetostrictive microvalve, as well as a beam element. And both of those deal both with simple and with TEM. So here's an animation with visual ease, what that would look like. We've also made some improvements with our material handling, as well as our electromagnetic analysis tool. We've made some major improvements. We've just rewritten a lot of the algorithms that it was using, just for better accuracy, and so it's usable for more applications. And then our biggest release this time is Parametric Analysis, a tool called Parametric Designer. So here we have that similar comb structure from before. And if we're going to perform an electrostatic analysis, we would do the following. We can take our existing VB script from the script database that we used in Blueprint, and then we select, so a little difficult to see. But in the middle, we select the parameter that we're looking to work with, and then set values for how we want to change it. Next, it will generate multiple layouts according to the parametric settings from the script. And then it will generate the 3D models and mesh them. At this point, you would select loads and boundary conditions for the 3D model. And then once you do that, it will run all of the simulations unattended using TEM and give you a result like this, which you can then either view in WaveRunner or 2D Viewer, one of our tools, or export your data for Excel. Just another quick example, we have a frequency analysis for a basic micro valve. And again, we change our parameters, generate the layouts, the FEM models, and then we can view our results at the end. These can take a little while, like it will take longer than a regular FEA analysis, because let's say you want to see 10 results, it will perform all of the simulations. How we've handled this in the past is we would use the TEM job manager. It's something we created a while back where you could import separate files and then run the jobs right after one another. But for that, you would actually have to go back in, re-edit your layout, recreate the 3D model, bring it into TEM again. It would take a long time. It wasn't a very popular tool. So with this, we've tried to take a lot of the work out of it. Next, lastly, just for system simulation, we've created those magnetostrictive elements not just for TEM, but for simple as well. So we've added these to the library and to the guide that explains all of them. We've created a new microphone element for simple. We've created a microphone macro model that can be used for noise analysis within simple. So this would be if you created your microphone within TEM and you have it exactly how you want it, you can bring it back into simple and perform a noise analysis and see how it would respond to different signals.
The reduced order modeling is going to be a part of the E8.
Which one?
Reduced order modeling. I think you can use simple to make a reduced order model from
yes.
3D.
So it will take the 3D, well, that would be the reduced order export from TEM. Yeah, the reduced order model, your simulation type in TEM, that's just one of the types. So you run it, and it will give you some files, and those are your reduced order model files. And then after plugging them into the simple template or running them through EDA Linker, you'll be able to run simulations using that model.
Is there any development for that specific part of it?
We have added VHDL. I know they support several other programs. We have a lot of our users using Cadence or Simulink. They're using that, so we've made it so it can work with that, and we're always expanding that. But as far as the process goes of creating the reduced order model, not much has changed. But when we add new features in simple, so the noise analysis features and the new elements that can work with your reduced order model, I mean, it definitely enhances what you can do with the tool. Lastly, we have NanoViewer. We actually released this in the very last build of 8.7. and we only released it to universities. It's basically a tool where you can import an SEM image or a set of them. In this case, we took one and we chose 3 areas to focus on. We set some values, so you would set some sort of measurement, like what your distance scale is, and if you're viewing at an angle or anything. And then it will create this 3D model where you can make measurements. So this is useful if you have a silicon sample and you're looking to see the surface qualities. If you're looking at a device, it can also work for that. If you fabricated a device and you want to see a 3D model of your SEM image for some reason, you can use this as well, provided that it's not numerous layers on top of one another, because it has no way of predicting that from an image.
Can you take an image on a rough surface and create a 3D model of it?
That is what we're trying to do with this. We're still kind of in the beginning stages.
That's a surface
Yeah.
feature. It's not a 3D feature, generally speaking. It's not a. I'm trying to say if I want to do finite element.
Oh,
rough surface structure. It's going to be tough, but my question: can I do something like that? Take an image of the surface and create a 3D solid of that.
I'd say with this, you could potentially get there, but you'll just run into a problem when you mesh it.
Yeah, I know that.
Okay. So, I guess no. You can't set a surface roughness in TEM, create a rough surface, and simulate it. With the 64-bit Expresso, you can certainly have a smaller mesh size, and if it's not very small roughness features, maybe you can get closer to your desired result, but not completely there. I think that's something that lies more in the meshing method. So maybe we're not quite there yet. But with this, we can create a 3D model that can open in Mesh Manipulator. So this is just something that we worked with a group at Peking University in China, and some of the students have come up with this, and we've helped them to incorporate it into IntelliSuite and make it into a real CAD format. So it's something new. We haven't had many people come to us with a real application for it yet, but there could be something there. So we've just been including it as part of the academic package. These are just some comparisons. All right. And that's all I have. All right. Thank you. Did you have any questions?